Examine the proteins in your body, the neurotransmitters in your brain, or the pharmaceutical drugs in your cabinet, and you will find they are organic derivatives of a single inorganic precursor, ammonia. When we swap ammonia's hydrogen atoms for alkyl or aryl carbon groups, we create an amine. The diverse chemical behavior of these molecules is controlled by the unshared electron pair sitting on the central nitrogen atom. To categorize these molecules, chemists use a rigid classification system based on the nitrogen itself. While alcohols are classified by the carbon holding the hydroxyl group, amines are classified strictly by counting the number of carbon groups bonded directly to the nitrogen. In a primary amine, nitrogen attaches to 1 carbon, in a secondary 2, and in a tertiary 3. Nitrogen can also use its lone pair to form a 4th bond, creating a quaternary ammonium salt, a positively charged cation balanced by an anion. In its neutral state, the nitrogen atom is sp3 hybridized. It adopts a trigonal pyramidal geometry, where the carbon-nitrogen bonds are compressed to an angle of roughly 108 degrees by the lone pair. The act of swapping a hydrogen atom for a carbon chain re-engineers the molecule's physical geometry and its chemical potential. That 108-degree bond angle is the result of a steric squeeze. Because the non-bonding lone pair occupies more space than a bond, it physically repels the 3 bonded groups, compressing the geometry. This geometry presents a stereochemical problem. While chiral carbons can be isolated into individual enantiomers, chiral amines usually cannot be resolved at room temperature. Due to pyramidal inversion, the nitrogen's mobile lone pair shifts, flipping the molecule inside out, exactly like an umbrella catching a sudden gust of wind. During this inversion, the molecule passes through a brief transition state where the nitrogen and its 3 attached groups flatten into an sp2 hybridized planar geometry. This process has a low activation energy barrier of approximately 25 kilojoules per mole. At room temperature, there is more than enough thermal energy to drive this flipping continuously. This inversion is a stereochemical consequence of the nitrogen's electronic structure. It demonstrates that the lone pair is not a static attachment, but a dynamic feature of a molecule whose geometry and reactivity are both governed by those 2 unshared electrons. We can observe the macroscopic effects of this structure through bulk physical properties. An amine's boiling point and water solubility are dictated by its capacity for intermolecular hydrogen bonding. Primary and secondary amines possess highly polar NH bonds. These allow the molecules to form networks of hydrogen bonds with one another. Nitrogen is less electronegative than oxygen, making these interactions weaker than the hydrogen bonds in alcohols. Tertiary amines lack NH bonds entirely. Without them, they cannot form hydrogen bonds, and the network breaks down. This creates a clear trend. For similar weights, alcohols have the highest boiling points, followed by primary amines, secondary amines, tertiary amines, and alkanes. Low molecular weight amines easily hydrogen bond with water, but as the hydrophobic carbon chain extends beyond 5 carbons, solubility drops sharply. By replacing hydrogen atoms with carbon groups, we reduce the molecule's ability to form intermolecular networks, a change that directly dictates its physical state. The chemical environment also controls basicity. Amines act as bases by using their lone pair to accept a proton or donate an electron pair. Based on the inductive effect, alkyl groups push electron density toward the nitrogen. Theoretically, basicity should increase as more carbons are added. In aqueous solutions, however, the real-world measurement deviates. Basicity peaks at the secondary amine and falls sharply for the tertiary amine. The missing variable is hydration stabilization. In water, the resulting conjugate acid must be solvated by water molecules to remain stable. The conjugate acid of a primary amine is highly stabilized because it has 3 hydrogens available for water molecules to bond with. A tertiary amine's bulky carbon groups create steric hindrance. This physical crowding blocks water molecules from solvating the cation, destabilizing the base. This structural interplay applies to aromatic amines too. Aniline, used to synthesize early commercial dyes, is a significantly weaker base than its aliphatic counterparts. In aniline, the nitrogen lone pair is delocalized into the benzene ring's pi cloud through resonance, this making it much less available to accept a proton. Aqueous basicity is a result of more than simple electron density. It is the outcome of a thermodynamic tug-of-war between inductive effects and the physical space required for water to stabilize the cation. In synthesis, the nitrogen lone pair acts as an active SN2 nucleophile, attacking electron-deficient carbons. In the mid-19th century, August Wilhelm von Hofmann attempted to use this by reacting ammonia directly with an alkyl halide. Hofmann's method had a major flaw. Once a primary amine forms, it is still nucleophilic and continues to attack the alkyl halide. This creates a runaway reaction, yielding a complex mixture of primary, secondary, and tertiary amines alongside quaternary ammonium salts. To prevent this overalkylation, chemists use the Gabriel phthalimide synthesis to produce pure primary aliphatic amines. The process begins with a bulky potassium phthalimide structure. As this flowchart shows, the massive rings physically shield the nitrogen, allowing only a single alkylation to occur. Once the carbon chain is attached, the intermediate is treated with hydrazine. This cleaves the protecting group and liberates the pure primary amine. This method cannot produce aniline, as aryl halides are inert to SN2 pathways. For aromatic amines, chemists must instead reduce a nitro group using a catalyst. To synthesize pure amines, chemists must use extreme steric bulk to artificially throttle the nitrogen's natural nucleophilic reactivity. In the laboratory, we identify unknown amines using qualitative tests that exploit the specific number of NH bonds on the nitrogen. Primary and secondary amines react with acid chlorides to yield stable amides. Tertiary amines do not react at all, as they lack the necessary hydrogen atom to complete the substitution. To isolate primary amines specifically, we use the carbolamine test, which involves heating the sample with alcoholic potassium hydroxide and chloroform. If a primary amine is present, the reaction produces an isocyanide. This product emits an intensely foul, toxic odor, providing a physical confirmation of the 1-degree amine. Nitrous acid provides even more specific results, reacting differently with each of the 3 amine classes. Primary aliphatic amines form unstable diazonium salts that immediately decompose. This releases nitrogen gas, creating aggressive, visible bubbling in the solution. Primary aromatic amines form stable salts at 0 degrees, while secondary amines react to form N-nitrosamines, oily yellow liquids that do not dissolve in water. This table summarizes how these reactions map to the different classes. Each result confirms the exact structural environment of the nitrogen atom. From boiling points and basicity paradoxes to synthetic diagnostics, the behavior of amines is predictable. It all stems from the specific steric and electronic environment surrounding that central nitrogen lone pair.